The content in this presentation is covered on pages 154 through 166 of your textbook, and it's meant to help you achieve learning objective number 23, which is to list and describe 4 mechanisms that cause air to rise. Be sure to skim these pages before you watch this video and read the chapter carefully before attempting the online quizzes. So why does air rise on some occasions to produce clouds and not in others? This is one of the variables in atmospheric sciences that sort of complicate the things that we were talking about in the last 2 lectures. That is not to say that this is a very complicated presentation. This one is back to the big picture stuff. So we're leaving the lab related material behind for a little bit, and we're talking about the real world. So breathe a little sigh of relief and just focus on the big scale, the large scale weather conditions here. The following 4 processes really cause the air to rise and generate clouds. So the way we can get uplift is around Washington State, we love to talk about orographic lifting. And that's where we see air being forced to rise over some sort of mountainous barrier. But we also see frontal lifting. In picture B here, we see warmer, less dense air being forced over the top of a wedge of cooler, denser air. Another process is in picture C down here is convergence, and that's the Florida Peninsula. And you can see that air is coming from the Gulf and from the Atlantic Ocean towards the center of that peninsula. And when those two bodies of air molecules collide, there's no place for them to go but up. That's a process called convergence, a pileup of horizontal airflow that ends up in movement in an upward direction. And then picture D here is convective uplift. And this is a very local form of uplift, and we'll see little puffball cumulus clouds form this way. So when you look up in the sky and you see those things that look like cotton balls, those are usually the result of very localized convective lifting. So what's happening there is there's an unequal surface heating that's causing air to rise higher in some little location. So for example, you could imagine a desert island in the middle of a warm ocean. Well, the warm temperature in the ocean might cause uplift of its own, but wait till you get to that hot beach sand on the island, right? A very different temperature surface. So we would expect to see convective uplift happening faster over the island than we would see over the ocean. Orographic lifting occurs whenever we have an elevated terrain, like a mountain, acting as a barrier to airflow. As the air descends or ascends, climbs up a mountain slope, we see adiabatic cooling, frequently generating clouds and often generating precipitation. In fact, many of the rainiest places in the world are located on the windward mountain slopes, so the side of the mountains that faces the wind. By the time air reaches the other side of the mountain, the leeward side, much of its moisture is lost. So if the air descends down the mountains, it warms adiabatically, making condensation and precipitation even less likely. So sinking air, we just expect it to not be cloudy and not be raining. As shown in the figure here, the result is called a rain-shadowed desert. And this is a model of the Coast Range in California, but the same thing happens to us in Washington State all along the Olympics and the Cascades. In the Great Basin Desert, we can see there are only a few hundred kilometers from the Pacific Ocean, a big mountain range. But the Great Basin Desert is cut off from the ocean moisture by the Sierra Nevada mountains. So we can also think of a number of examples around the world. The Gobi Desert in Mongolia, the Patagonia Desert in Argentina are more examples of deserts that only exist because they're on the downwind or leeward side of large mountain systems. If orographic lifting were the only mechanism that forced air aloft, the relatively flat central portion of North America would be a desert rather than the area that's known as the nation's breadbasket because plants grow so well there. Fortunately, it's not the case. In the central part of our continent, warm and cold air masses often collide. So cold air from Canada, warm air from the Gulf collide over that part of the country. And they produce boundaries between the two air masses that are called fronts. So these different air masses, instead of mixing together and forming, a warm air, the cooler, denser air is a barrier that the warmer, less dense air rises up and over. And that process is frontal lifting, or frontal wedging sometimes. And you should notice that weather-producing fronts are associated with storm systems called mid-latitude cyclones. And we're going to be talking about those a lot more in the near future. But they're known for producing a high percentage of the precipitation in the mid-latitudes. So we consider, in fact, mid-latitude climates to be something different from tropical and polar because of that mixing of frontal weather. Lack of mixing, I should say. When the wind pattern near the surface is such that more air is entering an air than is leaving, that's called convergence. The lifting occurs because there's this pileup of molecules around a low pressure system. So that to me sounds like a storm. So we think of a place where air is all piling up, and that can easily be a big red L on a weather map. But convergence as a mechanism of lifting is usually associated with storms, mainly mid-latitude cyclones and hurricanes. The inward flow of air at the surface of the systems is balanced by rising air, cloud formation, and usually precipitation. The example of Florida is an example of convergence. When we look at this particular part of our country, we can see convergence happening when there's some obstacle slowing the latitudinal flow of air. So when air moves from a relatively smooth surface like the ocean onto an irregular landscape, the increase in friction reduces the speed of the air. So the result is a big pileup of air, convergence. When air convergence, there's an upward flow of air molecules rather than just sort of squeezing them together. So it's not like people trying to cram into an elevator. These are small enough, light enough things that they all just kind of pile up. The Florida Peninsula is a classic example of the role that convergence can play in cloud development and precipitation. So on warm days, the airflow from the ocean towards the land occurs on both coasts of Florida. And that leads to a big pileup of air along the coasts and general convergence over the peninsula. That pattern of convergence and uplift is aided by intense solar heating of the land. And as a result, Florida's peninsula experiences the greatest frequency of thunderstorms in the whole country. On warm summer days, uneven heating of Earth's surface may cause pockets of air to be warmed more than the surrounding air. For instance, air above a plowed field will be warmed more than the air above adjacent fields of crops. Consequently, the parcel of air above the field, which is warmer and less dense than the surrounding air, will be buoyed upward. So these rising parcels of warmer air are known as thermals. And you can see birds like hawks and eagles using those warm air thermals to carry them to great heights where they can hunt for prey. Here in Washington, we use them on Cougar Mountain. Humans use them to hang glide as a way to fly. But the phenomenon that produces that rising thermal air is localized convective cooling. When warm parcels of air rise above the condensation level, clouds form, and on occasion you can get brief, low-intensity mid-afternoon rain showers from them. The height of the clouds produced in that way is somewhat limited because the buoyancy caused solely by the unequal surface heating is confined to, at most, just the first few kilometers of the atmosphere. The accompanying rains, although occasionally heavy, are usually short in duration and widely scattered. So a good source of what we know as sun showers can come from convective uplift. So use the course content here in the textbook on the Canvas site, as well as any of the reputable outside internet sources you can find to verify that you can answer these questions. If you can, you're in good shape for the midterm. If you can't, review the textbook, rewatch the video, and see if your abilities improve. If you're still completely stumped, start a discussion on the Canvas site or ask me for help.